Well, welcome back, Earth Space Science class. My apologies for the last video. It went longer than I meant to. I'll try to be a little briefer with this one. We're told that 25 minutes is maybe 30 is a good target for an online lecture, so I'll try for that. I have some helpers today. I'll see if I can move the camera around because I don't want to lift my helpers up. This is our one cat, Peaches, and Peaches is saying hi to you right now. Peaches is a little bit evil, so I don't want to pick up Peaches because she'll probably tear my arm to ribbons. And she really likes me. And then down here is our dog, Ellie. Hey, Ellie. Ellie. There's Ellie. She's saying hi. Okay, you can lay down. So just wanted to introduce you to my helpers today. I'm trying to go with different lighting in this room today in hopes that it will give you folks a little bit better picture. Today in this lecture, we're going to be talking about divisions of our world, and so we're going to go from basically outer space to the center of the Earth, journey to the center of the Earth. One of the more frequently redone, was it a Jules Verne novel, I think? Except we're going to do it in a little bit different way. We're going to be treating our world like an ogre. And so if you think about ogres, come on, there we go. There's our famous ogre. There's Shrek. Well, what do you know about ogres? Ogres have layers. And so that's how we're going to treat our world, like they have layers. And so, as I said, we're going to start from outer space, and since this is Earth space class, that's a good place to start, and move in. Before I do that, though, I just want to ask you a question, what I normally would ask the class. What are you mostly breathing right now? And so if you ask an elementary class, what thing are you mostly breathing right now? After they say air, you might want to say, depending on the grade level, you might want a little more detail. Well, what part of air are we breathing? And I think it would be very common for most kids, even maybe a lot of adults, maybe even most adults, to say, we're mostly breathing oxygen. Well, we're not. We're mostly breathing nitrogen. Nitrogen, if you look at your notes, comprises about 78% of the air we breathe. About 21% is oxygen, and 1% other. Boy, if you hear the news lately, mostly what we're breathing has got to be carbon dioxide because we're killing ourselves and heating up the planet and doing all these bad things. And it'll talk about how many tons, millions of tons of carbon are now in the atmosphere. But really, you got to keep in mind, however much carbon is there, it doesn't even make 1% of the Earth's atmosphere. Actually, the third most common thing, I believe, is argon, one of the similar gases to the gases we see in the like neon lights and such. So nitrogen is mostly what you breathe. Oxygen is second, and then 1% of a mix of other things, mostly argon, and a little tiny bit of carbon dioxide. Okay, so then if we are to go with a model of our Earth, one of the things you might want to ask your class is, and that I ask this class, if you were to jump from the surface right now, get really strong legs, and jump up to outer space, how far up would you have to jump? How far up is outer space? How many feet? How many miles? How many whatever? And so just think about that. If you look up at the sky right now, well, it's cloudy and snowing here, a little bit of snow. But if it were clear, how far up would you have to jump? How far up before the blue sky would no longer look blue, it would look just black because it would be made of different things, would not reflect light the same, would not look blue, it would look black. How far up is that? Well, if you look at an impression of our world, a model, if you will, of our world, this will give you some idea. Now, this illustration represents the layers of the Earth's atmosphere as circles. And of course, they're not circles. The layers get thick in some areas and thin in others. And so this is an average approximation. But if you look at, and also I'd have to define what is outer space. And that can be defined differently. Some would say that outer space is where light atoms are no longer pulled back towards the Earth's surface because of Earth's gravity, rather simply drift away aimlessly around in space. By that explanation, we would say the exosphere is the outermost layer of Earth's atmosphere. And on this diagram, that goes up to 190,000 kilometers. That's a good share of the way to the moon. In the notes, I've given you 10,000 kilometers as a conservative estimate, but you can just see that there's a good deal of variability and disagreement about how far up actually our planet ceases to have an effect on the layer of gas around it, and we enter outer space. So that exosphere, no matter how far out you think it goes, is the outermost layer. More commonly, and the more accepted definition for outer space, is anything beyond the Kármán line. Now, the Kármán line is not in your notes, but I want you to put it in your notes. The Kármán line is about 100 kilometers up, and the Kármán line is the line above which you can no longer fly a plane or a jet. The atmosphere is not thick enough to create enough lift so that an aircraft could fly there. You have to have a space vehicle, a shuttle, something that is rocket propelled. You cannot get, with an aircraft wing, air moving over the top of the wing takes a longer path than air moving under the wing. That creates lift and allows the plane to fly. There's not enough gas above the Kármán line to create that lift, and so planes and jets can't fly. And so most commonly, the Kármán line, 100 kilometers up, beyond that is accepted as outer space, and inside of that would be inner space. If you look at the layers then that are on your in your notes, the thermosphere is the next layer, and it's also fair to assume, I think, if I asked you, what does the temperature do as you go higher into the atmosphere? Now, I'm guessing that most of you, like most of your kids, will have experienced going to a mountain somewhere and have experienced, if it's high enough one, that it's quite cold up at the top of a mountain compared to the bottom of the mountain. If you go to Pikes Peak, for instance, which I'm guessing a number of you probably have, it might be 90 degrees at the base in Denver, and it might be 45, 50 degrees at the top of Pikes Peak. So it is a fair assumption to assume that the farther away you get from the Earth's surface, the cooler it gets, until you get into outer space where it must be just frigid cold. Well, yeah, usually it is, but if you're getting away from Earth's surface, you might also be getting closer to the source of our heat, closer to the furnace, that is our sun. So if you think about that, it might be logical to assume that it gets hotter as you get higher. Well, it depends on the nature of the layer. Some layers gets cooler, some layers it gets hotter. And it's not clearly one or the other. And so you'll see in your notes, it talks about the thermosphere, that the temp rises in the thermosphere compared to the mesosphere below it. And so then you go down to the mesosphere, and there the temperature falls in the mesosphere compared to the stratosphere. So there are changes that occur as you go up in these layers. I think, yeah. Okay. I'm not going to say much about the mesosphere because there's a layer of solid Earth that's also called the mesosphere, and I don't want to confuse things. Just know that that temperature fluctuation can swing one way or the other, either cooler or warmer, depending on whether you're getting closer to the sun, the nature of the gases in that layer, and those kinds of things. There's a layer here in your notes that is not on the diagram, though, that exists right in here, between the mesosphere and the thermosphere. It's called the ionosphere. And the ionosphere is a layer that has lots of ions in it. If you remember what an ion is an atom with a charge, either a plus or a minus charge. We'll get to that later. But you might know it better for what it does to you. I'm guessing you all have a cell phone, okay? And you've all no doubt had a call dropped. Sometimes it's just because of a closeness to a tower or not close enough to a tower or weather or something like that. But more often than you might think, it can be because of the ionosphere. You see, the satellites exist up here beyond the ionosphere, and so a signal has to travel from the Earth to a satellite back to Earth. That's how you have a phone call that is connected via a cell phone. If that ionosphere is particularly charged, for instance, because of a storm on the sun that blasts lots of ions towards Earth and charges up that layer, it is more frequent to have calls dropped or be of poor quality, or a signal on a TV set or a radio to be not of good quality because of the behavior of that ionosphere. So it's included in your notes because it's something that we commonly feel the effects of, even though it's not showing up here on this image of the layers of the Earth. The two last layers would include the stratosphere and the troposphere. The troposphere is what we live in. That's where most of Earth's weather is. And the stratosphere is just up above that. I think I have a picture here that I'm going to go back to. I should have loaded it already, but I didn't. And we'll see if this is the one I'm after. It looks like it is. Yeah, there we go. This is a picture of a thunderhead. A thunderstorm cloud. And I'm guessing most of you have noticed these kind of storms that are really big, and then they get this anvil-shaped top to them, like you see here. This is a visual evidence. This is some visual evidence that the stratosphere exists, because you see these clouds are growing really big, and they're getting up there, going through the stratosphere and into the or going through the troposphere and into the stratosphere, and the big winds in the stratosphere then are causing the cloud tops to be sheared off. There are what we call jet stream winds. If you've ever flown in a plane, you know that the jet stream, that those planes fly at like 30, 40,000 feet, and you'd think, why do they got to go so high? Well, some of it is because they're trying to get a really fast tailwind. These jet stream winds that occur in the stratosphere might be 100, 200 miles an hour. You catch a 200 mile an hour tailwind, you're going to get from A to B quicker, and you're going to spend less fuel doing it. Now, planes fly that high for other reasons as well, but to catch a good jet stream is one of them. Here's evidence that a jet stream exists as that thunderhead grows through the troposphere into the stratosphere and has its head sheared off, if you will, by those jet stream winds. The ozone layer is also in the stratosphere, and you may not have heard as much about the ozone layer recently. That's because the holes in it have healed, which is a good thing, and of course it's no longer newsworthy when it isn't catastrophic, you know, so we don't hear about it as much. And then lastly, as I mentioned, the troposphere, which is this lower layer where most of Earth's weather occurs. Another feature that I wanted to talk about is the hydrosphere. This is the layer of water. Now, I've talked about that one first before we get to the solid layer of Earth, because more of Earth's surface is covered by water, you know, like about 70% water, a little more than 70% is water, and a little less than 30% is land. It's interesting, you look at this, and the average elevation of Earth's surface would be almost 7,000 feet below sea level if you were to make everything flat, everything the same elevation. All of Earth would be covered to a depth of almost 7,000 feet if that were the case. So the hydrosphere, and if you think about it, of the water on Earth's surface, most of it is salt water. And this says 97%. It's actually a little bit more than that. It's 97%. Only 3% is fresh water. And of that fresh water, most of it is ice caps and glaciers and groundwater. Only a little tiny bit, this little tiny bit here, if we take that little bit and we blow it up, most of that is lakes and swamps. At any given time, only 2% of all the fresh water, which is only 3% of all of Earth's water, is actually in a river. But we're going to find that rivers and moving water is God's main tool for sculpting Earth's surface. Another way to make that point, if we look here, here's fresh water, and this is all of fresh water. Here's ice and groundwater, and this is the little bit that is not groundwater. So that's the hydrosphere. If we go back, I'm going to go back to Google Earth then. The biosphere is the layer in which life exists, and it's significant. It has an effect on, life has an effect on Earth's solid surface. I'm going to zoom in, and can you see this little dot right here? It's a little light colored dot in amongst the green dot. And if you look down here, we're at 1,109, almost 1,200 miles above Earth's surface. Let's go in just a little bit closer. The dot will show up a little bit bigger, I think. Okay. Now you can see that dot a little bit better. We're 725 miles above Earth's surface. So 1,000 miles up, you can see this dot. And I'm going to let you know this is something that humans have created. And if you look at it, it's right below the Great Salt Lake. This is the Bingham Copper Mine. And if we go down in it, whoa, that's a deep mine. And here's some trucks and vehicles mining away get after copper. If you look at the surface here, down here, I don't know if you can see this, but down on the side here, that's the surface of this pond at the bottom is 4,653 feet. If I go out, the top of the mine here, we're at 7,800 feet. So, you know, we're over 2/3 of a mile deep. This canyon, if we measure it, we don't want to measure it in feet though, we want to measure it in miles, just to give you a hint. If we go across the long axis of it, that is 5.2 miles across. That is a major hole. So human activity, you know, I could pull up a picture of a reservoir that's even bigger that's created because humans dammed a stream. So human life of any sort has a major effect on Earth's solid surface. Plus there's rocks made of things that were living, like coal, fossils, and limestone. Some limestones are made of things that used to be alive. Okay, we're going to just finish up by looking at some layers of Earth's solid surface. And the thing to remember is that as pressures increase, liquids solidify, liquids become solid. As temperature increase, solids become liquid. And those two forces, pressure and temperature, will dictate the nature of some elements of Earth's solid surface. Okay, so we'll start off with a cross-sectional look at Earth's surface. And here is all of Earth's surface from the core, which has a solid outer part and a liquid inner part, or a solid inner part and a liquid outer part, okay? And this is the mantle. And then up here, there's lower mantle, upper mantle. These are also called, this upper mantle is the asthenosphere, and part of the upper mantle is, and the lithosphere. So this little square right here, if we blow that up, okay, this is what we live on. So this little layer right here is what we live on. Below that is hot rock that is sometimes so hot that it's liquid, or behaves plastically or like Play-Doh. So we really truly live on just an eggshell. And it's really way too hot for humanity to exist or to take a journey to the center of the Earth, very far down at all. So we're going to start looking at oceanic crust first because, as I mentioned, oceans cover most of Earth's surface. And so if we look at oceanic crust, it has some characteristics that I hope to help define as we get into plate tectonics when we meet in person in lecture. So the first thing is that list that's in your notes, that oceanic crust tends to be thinner. If we radiometrically date it, it tends to date younger. It tends to be more dense. That means it's packed tighter together and heavier. So thinner, denser, younger, and it's made of a kind of rock we call basalt. Now that might not mean a lot to you yet, but it will. You'll become very familiar with basalt. Now we're going to contrast that with continental crust, which tends to be thicker. It tends to be older, date older. It tends to be made of granite types of rock, and it tends to be less dense. Now that's real important, that this continental crust, even though it's thicker, it's less dense. So this would be like rock, and this would be like styrofoam. You could make that analogy. That's going to become very important in explaining why Earth's surface looks like it does, and that's really where we're going. So in this oceanic crust, there are some features. I'm going to show you a map, a very earth-shaking map. This one came to being when I was just a youngster. So before I was born, humanity really thought that Earth's surface, if you were to hold your breath and go in the coast here at California, they thought you could just walk all the way across this flat, featureless ocean bottom and come up in Japan. That's what they thought of it. Then two people named Marie Tharp and Bruce Heezen. Heezen was a prof. Tharp was the administrative assistant, or the research assistant, I think. And she did, like most of these situations, she probably did the majority of the work, and Heezen probably took a lot of the credit for it, but I don't know that. Anyway, they used some echo sounding data from sonar that was developed mostly during World War II, and took another look at the ocean bottom. And there's a video clip that I'm going to have you watch here that I've included on Moodle that looks at that in some detail. But when they put their map together, and this is a copy of the Tharp-Heezen map, they discovered there were some features on the ocean floor that they had no idea existed. Predominant would be this feature right here. This is an underwater mountain range, and it's in the middle of most of the ocean, all of the oceans all around the world, all the way over to the Indian Ocean over here, comes back on in the Indian Ocean over to the Pacific Ocean, you know, the Arctic Ocean, Antarctica is just down here, and up into the Arctic Ocean up here. This was a very unique feature, and there are these cracks in it that stood out. And it was geologically very active along here. When we say geologically active, we mean there's volcanoes and earthquakes happening there. Okay, so that was one of the features. And then there are these features here that is really researched in the video clip that I want to show you. If we go to Google Earth, and I back out here, we'll look at some of those features. And I will have to, I don't know if you can see it on yours, but if we go to the Atlantic Ocean, oh, too far. You can see this mid-ocean ridge right here. I'm just tracking it along here. Now this is deep water. This is 12,000 feet below the surface of the ocean. And that crack, look at that crack. You can just see it all the way up. And Iceland sits right on top of it, and that's going to be important. And then it keeps going here all the way up into the Arctic. Okay? So that's that mid-ocean ridge. But then, if we go over to the Western Pacific, there's another feature here. And this is what the video is talking a lot about. And if we zoom in on this feature, this dark feature here, we'll see that we're no longer looking at foot depths. Let's go over here. So here's the island of Guam, okay? 400, so this is right at sea level here, you know, 2 feet, 50 feet, 60 feet above sea level. And then let's go just a little ways east of Guam and look, and I don't know if you can, I don't think you can see the depth, but we're looking at not 12,000 feet, we're looking at 25, 30,000 feet of depth. And folks, if you were rowing your rowboat over the top of this and you flipped a nickel over the side of the boat, that nickel would fall for the better part of a day before it hit the bottom of the ocean down here. That's how deep that is. Wow. So those are some features that we find in the ocean. It's not a featureless bottom. There are also these seamounts that we see, like the Hawaiian Islands here, okay, or here, and what we call the abyss and trenches and those sorts of features. And then there are continental features. Well, what does a continent got to have to be a continent, you know? Is Australia an island or is it a continent? Well, yes, it's both. There are just a few features. It's got to have a folded mountain belt, and Australia has the snowy mountains down here. And it's got to have a craton. Now, a craton is not recently deformed rocks. It's very old, very weathered-looking rocks. I'll show you some pictures here in just a second. A craton is made of two parts, a shield and a stable platform. The shield is those old rocks covered by sedimentary rocks. So if we were to look here at, these would be sedimentary rocks, okay? What did I say? A shield? A stable platform is covered by sedimentary rocks. I'm sorry. A shield is old rocks that are not covered by sedimentary rocks. My bad. Sorry if I got that confused. So very often, if you go to northern Minnesota, you will hear it referred to as the Canadian Shield region. And this is what old weathered rocks look like. And you can see these rocks are, the trees on them too are twisted and weathered, but these rocks are rounded, they're weathered, they're scarred, they're craggy, they've been around a long time. These lines are created as those rocks are acted on by forces that weather them and stretch them and change them. And when we look at a road cut, road cuts really get geologists excited. When we look at a road cut, you can see those swirly patterns through that indicate that the rocks were subjected to extreme forces of weathering and plate movement that affected them. That's what a shield is. That's what a shield rock looks like. If you cover these over with sedimentary rock, then that's what a stable platform is. Sorry if I mixed those two up. We're going to look at those two regions, those two areas, when we go to Taylor's Falls. And I've got to pause this for just a second. That's my phone. I'm going to just ignore that for a second and finish up this recording. Okay, we're going to finish up with this consideration of the last bits of layers here. The asthenosphere and mesosphere are listed there. I've talked about the asthenosphere. It's important to know that one is made of weak plasticky rocks. Capable of movement is the main thing, okay? Like Play-Doh. That's a good way to think about the asthenosphere. The mesosphere, underneath it, I said that's another layer there's a layer of the atmosphere that's called that. I'm not going to talk much about that except to notice that it's solid because pressure sort of wins the battle. That would be this lower mantle region here. And then you get to the liquid outer core. Temperature wins the battle there because that's liquid. And then pressure wins the battle on the other portion of the core, the solid inner core. And that's basically what it looks like if you were to take the roughly 4,000 mile journey from the surface of the Earth to the center of the Earth. All right, I think I'm going to stop there and try to stop this recording, which is kind of a tricky thing to do, it seems. And we'll pick it up in class then on Thursday of next week with in-class lecture. And I hope you folks have a good rest of the day.